This is problem 13-98. A shot putter tosses a shot at 40 degrees to the horizontal from a height of 1.8 meters. If the shot lands 15 meters away and its acceleration is 9.81 meters per second squared downward, determine A, the initial speed v naught of the shot, B, the maximum height h attained by the shot, and C, the distance d at which the maximum height occurs. Okay, so this is like almost a typical physics 170 problem, but it is a great foundational lead in to where we're going with like the rest of the semester. Basically, it's gonna have us deal with the trajectory motion, and we call it the rectilinear motion of a ball, of an object. And we're going to find all kinds of various heights. We're going to find acceleration, velocity, and position functions in both the x and y position simultaneously. And this is just a great all-encompassing kinematics equation right here, or kinematics problem. So let's take a look at the math. All right, so just like in the photo, we'll have our ball. It's starting at some initial velocity, okay? And there's some angle to the horizontal that this, I guess the shot put is starting out. And I'm not going to draw the guy and things like that. But there is already a 1.8 meter initial height. Okay, so that puts us with the origin coordinates at, I'm going to draw it just a little off from the actual point of origin so we can just see the difference. So imagine that the ball is actually on this y-axis. Okay, just didn't want to overlap things too much. All right, so oops. All right, so it says the shot putter tosses at 40 degrees. So this theta is 40 degrees. And already at the height of 1.8 meters, like I mentioned, and the shot lands 15 meters away. So we know that the distance is going to be 15 meters. All right, and its acceleration is 9.81 meters per second downward. Okay, so now we can start with the vectors. So our acceleration vector, both I hat and j hat, it's going to be 0 I hat, all right, and then it's minus 9.81 j hat, and this is meters per second squared. That should be an I. Draw the correct letter. Okay, and that's meters per second squared. All right, then we can integrate to get our velocity vector. All right, so there is going to be an initial velocity in the I hat and j hat direction. So the initial velocity in the I hat direction is going to be the horizontal component of the initial velocity that is, well, not given to us, but the direction is at least given to us. So we don't know the initial velocity, but we know it will be a cosine 40 degree vector. And that will be the I hat component of the velocity. And then plus, we'll have the initial velocity of sine 40 degrees. Okay, and then we still have the j hat component of integrating the acceleration, so negative 9.81 t. And then this whole piece here is the j hat, all right, and this whole thing is meters per second, the whole vector. All right, then we'll have the position vector. All right, so we're going to integrate the I hat term, which is the initial velocity t cosine 40 degrees. And then there's an initial position, which is 0 in the x direction. So we don't have to draw that. And we can do I hat. All right, and then we will have our j hat. So plus, and I'll just do it all as one piece here. We have an initial height of 1.8. So remember, this is the plus c's. So we're always having these initial values, these initial conditions that we have to take into account. And those are the plus c's of the integrations. And then our initial velocity is integrated so that we get v naught t sine 40 degrees. And then we're going to have the 9.81 divided by 2 t squared, which is 4.905 and t squared. Okay, and that whole thing is a j hat, and it's all in meters. All right. So they want us to find the initial speed v naught of the shot. Well, what can we learn about this system where we can discover what v naught is? Well, one thing we know is that the ball hits the ground when it reaches the 15-meter distance. That's one piece of information we know. We also know the ball hits the ground when it hits the 0-meter height, so the 0-meter distance in the y. So if we were to solve for the j hat component of distance and set this j hat component to 0, that would be when the ball hits the ground at 0 height, we'll have a v naught and a t. So it's two unknowns, so that doesn't help us. If we do the I hat component, then we'll have a v naught and t as well. All right, so neither one of those gets us to the solution, but they are two separate equations with two unknowns and the two same unknowns. So it's a system of equations. So what we have here is 0 equal to v naught t cosine 40 degrees. And then we have another equation, 0 equals 1.8 plus v naught times t sine 40 degrees minus 4.905 t squared. So we can solve for t and v naught using those two equations and get the two unknowns. So use your calculator, practice your algebra, whatever you need to do, but definitely if you got your graphing calculator, make sure you remember how to solve a system of equations in your TI-89. Okay, so t is equal to, or the TI Nspire, 1.713 seconds, and v naught is equal to 11.43 meters per second. So we just found the initial velocity and we happen to find the time, but wasn't really one of the things they explicitly stated. However, it was necessary in order to find the initial velocity. All right, so then part B wants us to find the maximum height attained by the shot. Well, when is the maximum height happening? Well, it happens when the velocity in the vertical is 0, because trajectory motion, a ballistic motion, will have the acceleration pulling down at a constant rate the entire time. And so the peak height is when the ball or whatever object is flying through the air has stopped going up and is immediately about to start going down. So that's at a 0 velocity peak. The 0 velocity, and that's peak height. So what we want to do is we want to take the j hat component of the velocity and set that to 0. So 0 equal to an initial velocity, which we know now is 11.43 meters per second, sine 40 degrees minus 9.81 t. All right, this is going to allow us to solve for the time that the ball is at maximum height. So 0.749 seconds. And then we can plug that time into the j hat component of position, and we know the initial velocity, and we can solve, and we'll get the height value. So the maximum height is equal to this j hat function of the r vector, but with values that we know. So 1.8 plus the initial velocity of 11.43, then times the time that we just calculated, all right, sine 40 degrees, okay, minus 4.905, and then times the time, 0.749 seconds squared. All right, and then we just solve. So we should get a height of 4.55 meters. All right. Lastly is we want the distance d at which the maximum height occurs. All right, well, that's the same time. So we just now put the same time in for the I hat component of the position. So we're going to get the distance mid, we could say. And then we plug in the 11.43 times the 0.749 seconds, and then cosine 40 degrees. And that should calculate out to be 6.56 meters. And that answers the question right there.